and then divide by 2a. And well, for our equation here, b is negative 6. Keep careful because it goes with the sign. So minus negative 6 plus or minus the square root of negative 6, quantity squared, minus 4 times a, which is 1, that's the leading coefficient, times c, that's the independent term. That's 1. Whole thing divided by 2 times 1, 2a. And well, let's just simplify this madness here. How about the smile rule here? Did I mention the smile rule before? No? No? Well, did you see this sort of a smile right here? It looks like a smile when I distribute the negatives. Well, what's that? Smile, be positive, right? That becomes a... I mean, it's so cheesy, I know, but it's catchy, right? So when they ask you why is negative terms a negative or positive, because of the smile rule. And although, well, that's not very mathy, but still catchy. Oh, 6 squared, that's a 36, right? And 4 times 1 is that 4. And that's over 2. 36 minus 4, that's 32. 6 plus or minus square root of 32. And divide that by 2. And I know what you might be thinking of dividing out the 6 by 2. However, we can't do that just yet because we need to have another coefficient that goes evenly into 2. All right. So lucky for us, we have this number 32, which can be factored. In other words, we can reduce that radical in a way that one of the factors is a perfect square, and then use the product rule for radicals. That is, well, one of the factors of 32 that is a perfect square, number one of them is 4, but another one is 16, 16 times 2. So 6 plus or minus the square root of 16 times 2 over 2, and then highlight the perfect square, and the square root of 16, which is 4, 6 plus or minus 4, root of 2, over 2. And only then we may go about the division by 2, because both the 6 and the coefficient of the radical, they're both divisible by 2. So 6 over 2, that's a 3, plus or minus 4 over 2, that's a 2, root of 2. And these are our two solutions to the problem. All right. So, but well, this is in terms of u, by the way. So again, so this is u equals to 3 plus or minus 2 root of 2. And well, now that we solved the problem in the world of u, let's go back to the world of x. So we recall that we did u equals e to the x, 3 plus minus 2 root of 2. And well, we can undo the exponential, in this case, by taking the ln on both sides. So ln, the whole thing. So that's x equals ln of 3 plus or minus 2 root of 2. All right. So what's this going to be in the end? Well, let's see. Are we going to get a good result here? Are we? Anyway, okay, we need to check both solutions in this case. Number 1, from here, x1 equals ln of 3 minus 2 root of 2, and x2 equals ln of 3 plus 2 root of 2. Okay, definitely that second solution is going to be an okay solution. And that's because that's a positive number plus another positive number. So that's going to be, well, approximately, I have the result, is 1.7627. But I'm not sure about the first solution, so let's find out using a graphing calculator. Okay, let's go ahead and do that, because I'm not sure about what I have on my notes, so that's kind of weird. All right, so ln of 3 minus 2 seconds square root of 2, and close parentheses, Oh, it's a negative number. It's all right. I mean, it's a number. It's not a negative number inside of the argument in this case, but the output is negative, which is fine. So let's go back, and that's approximately negative 1.7627, and that's when we round this to two decimal places precisely. All right. Okay. So, well, those are the two solutions. End of the problem right here. And let's see what's next. All right, so what is it? Okay, ln of x raised to the ln of x equals to 9. So we have um, well, not a bunch. I mean, it's a power that is also a natural log. All right. So don't freak out about having like, oh wait, it's another log to another log. Well, let's go back to the very basic type of expression. For example, ln of x to the third power. What would be an equivalent way to write this ln of x to the third power? Anyone? What is that again? Oh no, I mean it's still in logarithmic form without changing to exponential, by the way. Using one of the properties of log, that's a hint. 3ln, all right? 3ln x, all right? Essentially, smackdown rule for the exponent. We can do the same things here. This whole ln to jump in the front as a coefficient. And well, what are we going to have? We're going to have ln of x. I'm going to open and close parentheses times itself ln of x equals to 9. Okay? And well, so in this case, how about, okay, a quantity multiplied by itself, isn't it the same as saying the quantity ln of x, quantity squared, and that equals to 9. Now, side note, and let me write it down here. So the side note, ln of x times itself is equal to ln of x quantity squared, all right? Or rather the reverse. I think it makes sense if I write it the reverse. ln of x quantity squared is ln of x times itself. I mean, like any other quantity that we raise to the second power, it's always that quantity times itself. Or if it's cubed, well, times itself 3 times. Or is it to the fifth power times itself, well, 5 times, right? Now, ln of x squared, so this is fine right here. However, ln of x squared is not equal to ln of x times itself. Because this power right here, notice the position of the power. The power only belongs to the argument of the logarithmic function, not to the function overall, by the way. In fact, a better way to fix this, okay, let me go back to green to show the correct way, is to write it as ln of x squared instead. Because in this case, you know, it's kind of ambiguous. If you write it like this, there's a lot of place for ambiguity, like, well, is that 2 belonging only to the x or to the overall function? Well, so I think a better way is doing this. And if we have parentheses around, well, that around the entire function, well, then the square affects the whole function and not just the argument. And well, in this case, that's ln, or rather, 2 ln of x, right? I mean, again, coming back to playing with the different properties of logarithms here, right? And how do we use them? And of course, most importantly, how not to use them, right? Let's go back to the equation, and that's 9. That equals to 9. And in this case, well, so what do we have? We can make a u substitution, but maybe not necessary because it's not that kind of a weird thing to do. Take the square root on both sides. Don't forget the plus or minus on the right hand side. And that's ln of x equals plus or minus 3. And well, we can get rid of the ln by exponentiating both sides on the base e. So in this case, cancel, cancel. X equals e to the plus or minus 3. In other words, x1, that's equal to e to the negative 3, and x2 equals e to the third power. So two solutions in this case. All right. And again, keep in mind when you go back and review these notes or when you watch this video again, make sure to stress on what I wrote on the side, just so it works like a reminder about what to do and what not to do on when working with properties of logarithms. All right, what's next? There's another one. And for this one, I think we should do a u substitution. So number 1. And yes, I think you can see the difference here because here, notice how we have the square only affecting the x, and here we have the x affecting the whole function. How do we know? That's because we have parentheses around the entire function, and then the square affecting the whole thing, as opposed to the left-hand side of the equation, in which the 2 is only the exponent of the argument, the x in this case. All right. So to go about this problem, how about we use the smackdown rule for the exponent, make it jump here. Can I do that here as well? No, right? Because this actually is the same as saying log base 5 of x times itself, log base 5 of x. All right, so careful when do we do that smackdown, when it's okay, when it's not okay to do. All right, erase this. So that's 2 times log base 5 of x equals log base 5 of x quantity squared. Sounds good? And well, from here it looks like we can recognize some pattern here, some repetition. So notice how, oops, no, that's not what I wanted to do. Let me highlight this log base 5 of x with this log base 5 of x. It's the same quantity, it's the same expression, and we can do 2 times, oh, hold on, before doing that, how about we do a u substitution in a similar way that we did with the previous few examples. U equals log base 5 of x. So let's send this problem from the world of x to the world of u. So that's going to be 2u equals u squared. And well, notice how that equation is a simpler equation. It's a polynomial equation that we can solve by factoring in this case. Well, so that's the same as saying, well, negative u squared plus 2u equals to 0. But when it comes to having quadratic equations, you might want to have your leading term to be positive. So divide both sides by -1. There's no changes really to the left-hand side, to the right-hand side, because 0 divided by any number is still a 0. On the other hand, u squared minus 2u, and okay, equals to 0. And we can solve this equation just by factoring. Factor out the u. Factor out a u, that's going to leave us with u minus 2. Set it equal to 0, and by the zero product property, either u equals to 0 or u minus 2 equals to 0. That is, well, u equals to 0 is u equals to 0 already. No point. There's nothing else to do. But what about the second equation? U equals to 2. Okay, so now we have the solutions in the world of u. We solved the problem in the world of u. Let's go back to the world of x. So I'm going to back substitute for u, which in this case is log base 5 of x equals to 0, log base 5 of x equals to 2. And well, in order to undo the logarithm, we do the opposite of the logarithm, which in this case is to exponentiate both sides. However, in this case, that base that we use to exponentiate really matters because it has to match the base of the logarithm. So in this case, it's going to be exponential base 5, base 5, base 5, and base 5. This is going to cancel the exponential and the logarithm, and that's going to leave us with x equals to 5 to the 0 power, and a number to the 0 power is 1. That's one of the solutions in the world of x. Let's go about the second solution. So for the second solution, again, you might want to cancel the exponential with the log, and x equals 5 to the second power, which is 25. And those are the two solutions here. Let's see, what else do we have? Okay, the next one. Yes. Okay, the next one. Even though it contains like radicals and logs all over the place, well, it's more bark than bite, you'll see, because in this case we may not even need a u substitution at all, because we only have one single natural log term. I mean, I know there's a second natural log term here, but this one is a number. The only variable term is the one on the left hand side. So, and even though it looks weird, well, check this out. We can basketball the coefficient here, square root of ln of x equals ln of square root of 5 to the second power. All right? In this case, to the second power. So, oh, hold on. I think it's a misuse of parentheses. Never mind. And notice how we can cancel the exponent with a radical 2. That means square root of ln of x equals ln of 5. All right. Now, that's just a number, like 7, like 9, like 5, ln of 5. So, well, we want to get x by itself. How about we square both sides to get rid of the radical here? So if we square one side, square the other side as well. So that's going to be ln of x equals to ln of 5 squared, which is just ln of 5 squared. And again, as a side note, careful. Ln of 5, quantity squared, equals ln of 5 times itself, ln of 5. However, this is not equal to ln of 5. All right? And how about we do this using the graphing calculator? Okay, let me go back to the graphing calculator. I'm going to evaluate, okay, parentheses, ln of 5. And then, okay, let me close parentheses again and square this number. So that's 2.5902, and plus, well, 03 if we round to 4 decimal places, as we usually do for exponentials and logarithms. Now, let me write down ln of 5, close parentheses, times ln of 5, close parentheses, and click enter. Notice how that quantity is exactly the same, as opposed to instead, what was that? 2 ln of 5. Notice how the results are different. All right. So again, careful with the misuse of these properties, even though they look like powers, but When it comes to logarithms, again, it may be a little tricky. And again, well, lucky for us, it's all recorded. So when you see it again, when you review your notes, make sure to stress on this part. And well, from here, I guess we can exponentiate both sides by, well, in this case, the base of the logarithm, since it's an ln, base e. Now let's cancel e with ln, and x equals e to the ln of 5 to the second power. So that's the exact result. Of course, as usual, we want to express this result using 4 decimal places, and this is approximately 13.3336. All right. Okay. And I believe this is it for solving equations. I mean, there's more crazier equations that we can go about to keep practicing. I mean, even some of those nested logarithmic equations that we use the exponentiation more than once rather than having more than one logarithm. Maybe I will look for those notes and maybe I'll do one of those next time or something. And even systems of equations involving these logarithmic functions, those tend to be fun. Those are great. But I think this is more than enough for this class's purposes, right? So how about we do an application? An application to what's it called, to compound interest. But well, didn't we do that already? Yes, we did. However, all we did is to evaluate the function at the compound interest as a function to find out the accumulated amount of money given some principal investment at some interest rate for a determined number of years and compound it n times a year, whether it's twice a year, 4 times a year, which is quarterly, daily, weekly, etc. The different ways to compound per year. All right, but now I'm afraid the question is going to be different this time because, well, a couple invest 8,000 in a bond fund. The expected yield is 4.5%, which, by the way, we might want to write this in 0.045. Remember, we don't use percentages when working with formulas and all that. We change those to decimal forms. And the earnings are reinvested monthly. Well, that monthly is telling us that n equals to 12 because there's a 12 months in a year. All right? Use A equal P times 1 plus R over N to the NT to, what happened to read? Maybe it was 3 a.m. when I wrote this. Anyway, I don't know. To write, all right? I meant to write. Yeah, I meant to write a model representing the amount A in dollars in the account after T years. The value R is the interest rate and N is the number of times interest is compounded per year. Like I mentioned, whether this is monthly, well, 12 times a year. Is it weekly, 52 times per week, or etc., etc. Or if it is continuously, we use the other function, the exponential function, that is the PERT formula. But well, in this case, it's not continuous. It's actually 12 times a year. It's monthly. So number one thing we want to do, so A equals P, which is the principal, the initial investment. That's 8,000. 1 plus R, that's the percent rate, 0.045. Over N, which is 12, raised to the 12 times, what's that? T, right, for now. 12T. Because we don't know how many years, actually. In fact, that's the question. All right, that's the question. That's part B. Oh, well, actually, you know what? Let me simplify this madness inside of the parentheses. So that's 1 plus 0.045. Divide that by 12. So 1.00375. That's 1.00, what is that? 375, right? And raise that to the 12t. Well, that looks like an exponential function indeed. However, well, the base of the exponent this time is not a nice number. It's not like 5, like 7. However, I mean, it's a weird number and it's okay. It's a valid number. That exponent, that base of the exponential is not a 0, which is one of the restrictions for the exponentials. And it's not 1 as well. So, I mean, it's a little bit more than 1. So for sure, we will see some increment, some function increasing, some growth in this case. And well, that's the expectation, you know, when you invest money in an account and then you get some dividends after a while. I mean, you should get an amount of money that is larger than what you invested, unless it's interest when you are when they charge you to have an account. Well, in that case, this base of the exponential, the bank will use to treat your case in this case, well, will be a number below 1 to actually discount money from your account, right? So watch it when you're making investments and the like. Make sure those percentages represent growth and not decay, because otherwise they will take your money instead of giving you money, all right? So now the question is how long it will take the initial investment to double. Well, so it's kind of a cryptic sentence, but well, to double, if initially the couple invested 8,000, to double, that means to have those 8,000 to become 16,000. All right? So that's going to be the accumulated. So after how many years will those $8,000 become $16,000? So I'm going to replace this 16,000 here where the A is, and solve the equation. All right. So that's a 16, not this one. 1600, I mean 16,000, not 100, come on. 8,000 times 1.00375 raised to the 12t. And well, let's solve that exponential equation. It shouldn't be a big deal except for maybe the funky numbers. I mean, by not being a big deal, I mean it shouldn't be because it's not one of those equations that contain more than one exponential term, like the ones that we just finished working on. It's one of those baby equations with one single exponent here. So let's see. Let's do all the algebraic steps first, and then we punch everything in the graphing calculator to get the result. So in the meantime, let's divide both sides by 8,000 to cancel this. That's going to give us 2. And well, no wonder, because that's to double, right? That's 2. And that's a 1. Okay, I'm going to leave a space. I'm going to leave some space. 1.00375 raised to the 12t. All right, and the reason I left that space in here is because we're going to do, you know, at this point, that what operation to get rid of the exponential so we can solve for t. And that operation is the logarithmic operation. And again, you have two options. You can take log on both sides, that is log base 10 or the common logarithm, or you could do the ln, whichever you prefer. It's going to give you the same result. So I'm going to do ln. So, well, that ln Well, it's just ln, okay, for now. But number one, what's gonna happen when we do the ln? When we have this ln, let me make some space here. I knew I was gonna need more space. This power becomes a coefficient by the Smackdown rule for logarithms, right? So that's going to become ln of 2 equals to 12t 1 point times 1 point ln, right? ln of 1.00375. And well, this now becomes a baby linear equation. All we need to do is divide both sides by this funky number right here, that is by 12 ln of 1.00375. Sounds good? Oh, do that on both sides, of course. So that's a 12 ln of 1.00375. All right, divide these two factors out, and t is precisely this madness here, ln of 2 over 12 ln of 1.00375. Well, of course, that's the exact result, and we could rewrite that 1.0375 as a fraction, but well, in this case, we don't want this result. The reason why we also learn how to simplify this using a graphing calculator is because when it comes to applications like this, especially applications to money, to business stuff, well, we want to know the number in as money. I mean, as well, that's about, yes, as money, but more like an integer, something that we can have an idea of the magnitude of what we're dealing with. Well, let's go ahead and put this in the graphing calculator. However, be careful. In fact, I'm going to do this the wrong way so I can show you the common pitfalls when punching this in the graphing calculator. All right. Some calculators are pretty nice and just type like a quotient. However, not all of them. So that's going to be okay. Number one, ln of 2. Close parentheses, make sure to close parentheses, because otherwise if you do the division, whatever you do will remain in the argument of the logarithm of the numerator. So make sure to close that parenthesis and divide by 12 ln of this madness. 12 ln of, what's that? 1.00375. But this is wrong. How can we tell this is wrong? Look at the result. I mean, okay, let's observe that result. That's 2.16 times 10 to the negative 4. I'm going to write this into 1, 2, 3, 4. So that's 0.000216 years. Okay. Would it make sense to double my amount of money in this amount of time? I mean, we wish, right? I mean, pretty much, so how much is this in years? Well, I'm going to say maybe even minutes, right? So that's not how it works. So that's how you can assess your results and see how they make sense. So in this case, well, again, that's what I did this wrongly. Because in this case, you need to make sure to have parentheses around the whole denominator. So I'm going to repeat the calculation to ln of 2 and divide that by, okay, open parentheses first for the overall expression below. That's a 12 ln of 1.00375. Close parentheses first for the argument of the natural log, and then close parentheses again for the whole denominator, and see what we get. So 15.43 years makes more sense, right? I mean, especially at that rate of interest, which is only 4.5 interest. Of course, I mean 15 years makes more sense. All right. What is that? 15 what? 15.4. So 15.4 years. Well, that point 4, if that point 4, we multiply that by 12, 12 times 4, is that 48? That's basically 4.8 of a year, basically halfway through the year would be. All right, around, well, if it's January, sometime by the end of May or maybe in June, I don't know, within those days, those $8,000 will become $16,000. All right. And I think this is also the end of the section. How about we go and look at the next section? And the next section is about still solving exponential and logarithmic equations. However, we are going to apply this. Well, we already did one for an application problem for, what's it called? For interest. However, this time we're going to apply this solving of equations to, well, for a specified variable. We haven't done that yet. All we've done, we just solve for x. In this case, we have an equation with more than one variable and solve for that variable. Yes?
Have you posted this?
Yes, I posted it last night.
I tried to look for it last night.
Really? Oh, interesting. I'll check it out. I don't know what happened. However, you know what? I think I'd rather stop here, and for sure we can